chord, okay? Now, as you have, when you have a zero denominator like this, you try to uh, cancel out the zero denominator and see what you have. And here you can easily calculate the limit. In this case, you have again zero denominator. You multiply by 1, but you put the conjugate of this expression in the numerator, and then you can cancel out x's, and you get 1 over 20 as the limit. Okay? So let me just repeat this again. It's important how the function behaves as you get close to some number c or x of 0. Whether the function goes to a constant value or not. That's the important question. Let's continue now. Okay, now we have seen this example. It was in the previous slide. Okay, so this function is not defined at x equals 1, where y is actually t, but the function is not defined here. So you put an open dot here. However, the function, as you can see, as you approach one from the right or from the left, it goes to a constant value. And actually, you can calculate this constant value from this. You just cancel out 1 when you factorize this, and that gives you the limit. So that's a pictorial representation of this previous figure. Now let's look at these functions. You have h, which is shown with red. You have g, which is shown with yellow. And now there's a blue function f between these two functions. It's greater than or equal to g in this interval and less than or equal to h. Now, let's call the sandwich theorem for finding the limits. If your function is between two other functions, g and h, and if these two functions have a limit, as you can see, they have a limit, both the yellow function g and red function h has a limit at c, and this limit, let's say, is L. Then you immediately know that your own function, which is shown as blue, has the same limit. This is called the sandwich theorem for finding limits. We are going to use this theorem later on to find the limits of functions. And that's how the theorem is. Suppose that g of x is less than f of x, which is less than h of x, in some open interval containing c. Okay, so if you try to calculate the limit as x goes to c. It may not be true at x equals to, this might not be true, but for all other values of x, this inequality must hold. Then, if limit as x goes to c of g of x, and limit as x goes to c of h of x is equal to L, then your function must have the same limit. Okay? Just remember, this inequality may or may not hold at x equal to c, but it has to hold for all other values of x within this open interval. So when this is true, you immediately know that the limit of your function as x approaches c is L. There are other examples that we can give here. And let's look at this example. Y is equal to 1 plus x squared over 2. That's a parabola which opens upwards. And at x equal to 0, it has value 1. It has a limit. There's no problem with this function. This function, y is equal to 1 minus x squared over 4. It's again a parabola which opens downwards. And when x is equal to 0, it's again 1. So both the red and yellow functions have limit 1 as you approach x of 0. Your function y is equal to u of x. Could be anything like this. But as you can see, it's less than this function, red function. It's greater than the yellow function. Since these both functions have limit 1 as x approaches 0, this function must have limit 1 as x approaches 0. And you can just put out other examples. For instance, y is equal to sine theta. So y is equal to sine theta is less than y is equal to absolute value of theta, and greater than y is equal to absolute value of uh, minus the absolute value of theta. So this is the yellow function and this is the red function. This is our own function. This inequality is called. So you know that as theta goes to 0, then the limit of your function in sine theta is 0 because it's squeezed between these two functions. And another example is this. Y is equal to 1 minus cosine of theta. It's less than y is equal to theta, and it's greater than y is equal to 0. Okay, that's the yellow function here. Y is equal to 0 on the theta axis. Again, my function is squeezed from between these two functions. As theta goes to 0, red function has 0 and yellow function is 0. So the limit of this function must be 0 also. So that's the sandwich theorem, and let's use it. Okay, now let's come to the precise definition of a limit. Okay, that's the definition. Remember, before we had a crude definition of the limit as the function approaches to a constant value of if x is sufficiently close to c. These are not mathematical definitions. And this is the precise definition. F of x we define on an open interval containing c, except possibly at c itself. At c, x may or may not be defined. I don't care about it. We say that the limit of f of x as x approaches c is the number L, and write this limit as x approaches to c, f of x is equal to L. We write this if for every real number epsilon which is greater than 0, there exists a corresponding number delta greater than 0, such that f of x minus L is less than epsilon whenever x absolute value of x minus c is less than delta. Since it's an absolute value, it's obviously greater. But if you look at this, this is a symmetric interval about c with delta as length. Okay, for every x in this interval except c, this must be true. If you can prove this, then you're done. That's the precise definition of the limit. You can give me epsilon as small as you want, 10 to the minus 25, let's say. If I can find delta so that for all x interval in this interval except c, of course, if this holds, then you're all done. You can write this. You can say that the limit f of x as x approaches to c is L. Okay, so that's the precise definition of the limit, and we are going to use this to prove the limits of certain functions. Okay, let's start with a simple one function. Y is equal to 2x minus 1 and near x equal to 4. So I'm going to approach 4. Now at 4, the limit is 7. suppose that we want y minus 7 less than epsilon. You know that this function has a limit, and actually as x approaches 4, you just substitute. That's a polynomial. That's 8 minus 1 L is 7 in this case. We know this because there's no problem. We can do this by substitution 4 instead of x. However, can we prove it? I mean, if given for any epsilon, can we find the delta so that when x is in this symmetric interval, y minus 7 is less than epsilon? Now, the way to do it, you open this. Okay? Y is 2x. First, y is equal to 2x minus 1. So you have 2x minus 1 minus 7. That's 2x minus 8 less than epsilon. So if you open this up, you get this inequality. And this inequality and these are the same as we have seen before when we reviewed the inequalities of real numbers. Okay, so since that's true, you just add 8 to each side. Okay, so you have minus epsilon plus 8 divide is less than 2x, which is less than epsilon plus 8. Now you can divide everything by 2. So minus epsilon over 2 plus less than x, and epsilon of plus 2 plus epsilon over 2 plus 4 is greater than x. So what you have here, if you subtract 4 from each side, then you have minus epsilon over 2 less than x minus 4, epsilon over 2 is greater than x minus 4. Now what does this tell you? You choose delta is equal to epsilon over 2. When you choose delta as epsilon over 2, that's greater than x, absolute value of x minus 4. That's obvious here because that's a symmetric interval. And that's true then. That's true, that's true, that's true, and that's true. So this implies that for any epsilon greater than 0, you can choose delta is equal to epsilon over 2, and the condition this will guarantee that y minus 7 is less than epsilon. Okay, that's the proof of the fact that the limit as x approaches to 4 of this function 7. Okay, so you can algebraically find delta. Okay? Let's look at another example. Limit as x approaches to 1 of 5x minus 3. If you directly substitute x is equal to 1, 5 minus 3 is 2. Now for any given epsilon, what can I choose for delta? So I have to find out the symmetric open interval around 1 such that for any x in this interval except 1, y minus 2 is less than epsilon. So again, that's my function. That's the limit L. That's L is 2 in this case, less than epsilon. That means 5 times x minus 1, take 5 out, is less than epsilon. And then x minus 1 is less than epsilon over 5. So that should be delta. That's the highest delta I can find. And anything less than epsilon over 5 will do also. You can epsilon over 6, epsilon over 7. Anything less than that will do also. That. But the maximum delta you find here is epsilon over 5. It's good to try to find the maximum delta all time. Okay, so now let's show this pictorial. That's the function 2x minus 1, and we approach it to 4. and the limit is 7. So what you're doing algebraically is here epsilon is given as 2, okay? Because 7, that's the limit, is between 9 and 5. So what we calculated algebraically was you put delta epsilon, that's 1, so around 4, 1 and delta, so that's the interval. For all the x in this interval, here 4 is included also, but it might not, the function might be defined somewhere up here. It doesn't make any difference. I can put y is equal to 2x minus 1, but when x is equal to 4, then say that's 10. So the value is here. But it doesn't make any difference. I can still prove that for all x in that except 4, f of x minus L, which is f of x minus 1, L is 7. That's less than epsilon. Here the epsilon is 2. You can put lower value, you can give lower values of epsilon. Actually, you can give any positive number for epsilon, and still in this case, you can find delta as epsilon over 2. And then you're all done. You prove that the limit of this function is 7 as x goes to 4. So, for instance, that's for any function. Suppose you give epsilon 1 over 10, okay? So that's your L. So f of x minus L less than epsilon means that f of x should be in this interval. L plus 1 over 10, that's an open interval. L minus 1 over 10. So your function value, what must be for all x. Now you find delta from C, that's C minus delta and C plus delta. That's a symmetric interval around x. Now for any x, the function must be in this value. For any x in this interval, the function must be within this interval. And you can squeeze this interval here. You can put 1 over 1,000, 1 over 10,000, 1 over a million. Still, you will find a delta. You should find delta. So that for any x in this interval, except c, of course, your function value must stay here. Okay, so as you reduce epsilon more and more, of course, the delta will use more and more here, but still, you should find this delta for any function given in order to prove the limit. Same here for any epsilon. So when you are given epsilon, the function value within this plus epsilon minus epsilon. That's an interval. So you are trying to find now delta symmetric interval around C. So for any x in this interval, the function value should be. Then you're all done. You can do this for any epsilon. If you can prove that you can do this for any epsilon, you're all done. And we did this. For in one of the examples, we find delta should be 1 over 2. That's the maximum delta you can get. And in the other, delta must be epsilon over 5. Okay, that's the 5 minus 5x minus 3 is equal to 1. The limit is 2. So this could be anything. Epsilon could be put in for epsilon. Delta is epsilon over 5. So 1 is here. That's an open interval 2. 1 plus epsilon over 5 and 1 minus epsilon over 5 will give me. I will finish the proof that this limit is 2. that was a pictorial representation of what we did algebraically in finding delta. Of course, this is sort of geometrically finding delta. The other one is the algebraic finding delta. Okay, now I try to do it for y is equal to x, which is a very simple function. As you approach c, your limit is c, we know that. So what you do is given epsilon, your function value may be in these points. Okay, so I said delta is less than or equal to epsilon. If delta less than or equal to epsilon, you will be on done. Here, delta is less than epsilon, but you can put delta is equal to epsilon here too. So that's your epsilon. So here for function algebraic, you will find delta is equal to epsilon, and anything less will do it because you will be still in this interval plus epsilon and c minus epsilon. C is your limit. So that's a simple function, and C find out. Now here, look at the constant function. Y is equal to k for all values. So we can put d anything, any positive number. It doesn't make any difference. It could be big or small because your function has a constant value. So the limit always is the same, k. Whether you approach c or any other number, the limit is k, and delta you can choose any positive number will do. It could be very small, it could be very big, because the function has a constant value. So that was a simple one kind of method also. Okay, now let's look at this function. Okay. Y is equal to square root of x minus 1. Okay. Now you want to find the limit as x approaches to 5. Okay. We know that the limit, there's no proof. Again, x is equal to 5, 5 minus 4, square root of 4 is equal to 2, so limit is equal to 2. Okay? But now, suppose you are given epsilon as 1, so that's L. So you should be, your function value must be between 3 and 1 here. If epsilon is equal to 1, that's your L, f of x minus L absolute value should be less than epsilon, which is less than 1. So your function should be here. What can you choose for delta? That's a question. Of course, when you look at this, this cuts the graph of the function at this point, 10. If you put x is equal to 10, that's 10 minus 1, 9, and 3, square root is 3. If you look here, you put cuts it here, 1 cuts it here. So if you put x is equal to 2 minus 1 is 1, so that's here. Now, around 5, there is this input, which is okay for you, with length 5, and there is this interval with length 3. But what we are asking is a symmetric interval around 3. And so you have to choose this portion. Now let's show this algebraically. Okay? Let's calculate delta algebraically. Okay, so first step, f of x minus L less than epsilon, any given epsilon. F of x is square root of x minus 1. L is 2 in this because we are going to look at as x approaches 5. Okay, so L is equal to 2, so I can open this up like this. So add 2 to both sides, to every side. So we have 2 minus epsilon square root of x minus 1, which is less than 2 plus epsilon. So that's the inequality we have. Now I can take the square of this, because this equality doesn't spoil, is not spoiled when the square. These are all positive numbers. So I take the square 2 minus epsilon square, and I add 1 after I take the square plus 1 is less than x, which is less than 2 plus epsilon squared plus 1. Here I am assuming that epsilon is less than 2. Now the second step is to find delta, which will be symmetric about x of 0, which is 5. So I subtract 5 from each side. Okay, from here you have minus 4 here, another minus 4 here, because 1 cancels out. So x minus 5, 2 minus epsilon square minus 4, and 2 plus epsilon square minus 4. Okay, now that's not a symmetric interval around 5. Okay, so if you just calculate out epsilon times epsilon minus 4, x minus 5, epsilon times epsilon plus 4 you get here. Okay, of course, now this is again not a symmetric interval around 5, so I take the minimum distance from 5, because these show the distances from 5. As in the previous figure, if epsilon is given as 1, that's if epsilon is 1, that's minus 3, and that's 5 times 1, that's 5. So 5 more. The distance from 5 is 10 if epsilon is 1, and the distance from 5 is p here. This is minus 3 as a limit, but it tells you the distance also, that's absolute value of minus 3. And you get exactly the same here. Okay, this is the interval on the right-hand side. This is the interval on the left-hand side. Now, which one you choose for a symmetric interval? Because the lengths must be the same. If you choose this interval with length 5, you then go to 0 and your function value is not within these limits. So you choose the smaller distance, that's 3. And so here what you decide is epsilon times epsilon minus 5, but with the absolute value, because that's here is the distance. That's the minimum distance from 5. As you see here, that's a bigger distance, so you cannot choose this. If you choose this, then this will not be satisfied, because you're out of the region where your function value must be. Let me show it again, that's important. Okay, if you choose this interval to be symmetric about 5, which has length 5, you're right here. Okay, you're right here, and your functional value is not within this yellow-green region. So what you choose is, you choose the minimum distance, 3. So, and if epsilon is not 1, you always know what to choose. Epsilon times absolute value of epsilon minus 4 is the one that you choose, because this is greater than this as an absolute value. Okay, any questions here? So that's how we find algebraically. We always choose, we look at the bounds on x minus 5 or x minus x of 0, if you say it in general terms. And these give, when you write it like this, when you have here x minus 5, these give the distances from 5. You will put the smallest one. Otherwise, put the big one as your delta, you're out of the limit. This this is not true. F of x minus L is not less than epsilon. If you choose the small one, you have. Okay. So, any questions up to now? Let's continue then. Now that's a summary of how you find delta algebraically for a given f function L, the limit c x of 0, c in this case, and epsilon. So as we did before, as you've seen before, you have this whenever x is in this symmetric interval, except x is equal to c. You open the interval a, find an open interval AB containing c, on which the equality holds for all x except c. Now, the value of f at xc does not include the existence of the limit. So this inequality should hold for all x except c. Then you find that delta centered at c in this interval. Now, the interval AB is what we have here algebraically. Now that's the interval AB. It comes from opening this up, being squared, etc., manipulating so that you have x minus c, c is 5 in this case, and so you have this interval, and that's the same thing, AB is this. Then you choose delta within this interval, and you choose the maximum delta is the smallest of the distance from your C to B or A. And then you are all done. It sort of summarizes what we have there. Okay, let's now look at this function. Y is equal to x squared. We want to find the limit as x approaches 2 of this function. And of course, there's no problem. The limit must be 4. And suppose you are given an epsilon. So that's 4 plus epsilon, 4 minus epsilon. Please cut your graph at these points. Okay. So your AB is here. Okay? If these are equal length, there's no problem. So you can choose delta is equal to 1. Here, that won't be 4 minus e and 4 plus e here. So you have to choose the minimum one. So let's try to do it algebraically. Suppose you have this function, f of x equal to a dash, if x is not equal to 2. At x equal to 2, f of x is equal to, that's exactly the same as this function here. At 2, the function is not defined. Actually, it's defined, but it's here. However, I don't care about this because my inequalities should hold for all x except 2. I don't care about it. So that's what I'm going to do here algebraically. So my function is s squared, the limit is 4. If you substitute correctly, I want this to be less than epsilon. If you open this up, you have here 4 minus epsilon x squared 4 plus epsilon. I take the square root because you want to find an x here, not x squared. So you are going to build a symmetric interval about x is equal to 2. Okay? So you take the square root, you take, because we assume here that of course epsilon is less than 4. That's sort of obvious because you are taking the square root of 4 minus epsilon and 4 plus epsilon. So that's what I get here. Now let's subtract 2 from each side because that's c is equal to 2. So x minus 2 here, which is greater than the square root of 4 minus epsilon minus 2 and less than 4 plus epsilon. Okay, now as you can see, this number here is negative because 4 minus square root of 4 minus epsilon for any positive number epsilon is less than 2. So that's a negative number. This is a positive number because 4 plus epsilon is always square root of 4 plus epsilon is always greater than x, greater than 2. So what you do is you take the absolute values and absolute value of this compare. So your delta is the minimum of this. Okay? And so if you choose as the minimum of this for a given epsilon, of course you have to calculate this. Then when you choose the minimum, then you roll down. That maximum delta you can have. So that x squared minus 4 is an epsilon. Okay, for certain cases, you just write this. So that's actually AB. That's mentioned in the previous paragraph. A is negative, but it shows if you take the absolute value, it shows the distance from 2. And so you choose the smallest one. The absolute value of this is minus 4 minus epsilon. Now that's a positive number. That's a positive number. 2 plus epsilon minus 2. You choose the minimum of these two numbers, then you roll down. Yeah.
X kare eksi 4 neden?
X kare eksi 4 niye yaptım anlamadım ben.
Şık 4 yaptık. Limit 2'den fx 4'ü çözerken.
Bizim fonksiyonumuz x kare x 2'ye eşit olmadığı zamanlar. Ama
Evet.
x 2'ye eşit olduğu zaman 2'ye eşit. X'in 2'ye eşit olmasına bakmıyorum. Ben x'e sağdan ve soldan giderken fonksiyon bir sabit değere gidiyor mu gitmiyor mu diye bakıyorum. Değil mi? Şimdi x kareye doğrudan doğruya 2 koyarsan bu tanımlanmamış olsa bunun limitinin 4 olması lazım değil mi? O zaman L 4. Bu da fonksiyonu.
Evet.
Bir dakika şekilde de göstereyim sana onu. Şimdi şöyle. Burada gördüğün gibi benim fonksiyonumun değeri 4 değil burada. Burada boş bir nokta var. Burada değeri şu. Yani x2'de şimdi ben bununla ilgilenmiyorum. Çünkü ben 2'ye yaklaşırken fonksiyon nasıl davranıyor diye bakıyorum. 2'de ne olduğu derdim değil benim. 2'ye buradan soldan veya sağdan yaklaşırken benim fonksiyonum grafikten de görüldüğü gibi 4'e gidiyor. Değil mi?
Evet.
O zaman gittiğine göre 4 artı epsilon burada, 4 eksi epsilon burada. Şimdi benim değerimin burada bir aralık seçtiğim zaman, ekseninde bir aralık seçtiğim zaman, iki etrafında simetrik bir aralık seçtiğim zaman fonksiyonun değeri burada olması lazım. Bu bant içinde. Şimdi 4 eksi epsilon burada kesiyor fonksiyonu. 4 eksi epsilon da burada kesiyor fonksiyonu. Şimdi bu aralık benim için önemli. Bu aralıkta da minimum olanını bulmam lazım. Bu aralık 4 eksi epsilon, 4 artı epsilon 2'nin etrafında. Ama x eksi 2'de yani 2'nin etrafında bulmam lazım. Bunun için burada ne yaptım? Bunu elde ettikten sonra x eksi 2 iki tarafa da 2 çıkardım ki. Yani şimdi x eksi 2 delta'dan küçük olacak diyorum. Bu bu b dersen eğer bu interval içinde hangisi minimumsa bunlardan? Şu ve şu. Bu negatif sayı, onun için bunun absolute value'sunu aldım. Bu zaten pozitif sayı, absolute value'su kendisine eşit. Ya bunlardan hangisi küçük, onu seçeceğim. Ve bu interval içinde kalacağım o zaman. Ha, x eşittir 2'de bu interval içinde değilim. Ama ona düşmüyorum ben. X'e yaklaşırken ne oluyor ona bakıyorum. Onun için eğer bunların minimum alırsam bu doğru. Bu da doğru, bu da doğru, bu da doğru. O zaman bu da doğru. Benim
Tamam.
limitim o zaman 4. Shall I say it in English again? The question asked by your friend was, why did we put here 4? My function is this. At 2, it's equal to 2, not equal to 4. But when I look at the figure, as I approach 2 from right and left, my function approaches 4. And I can see this geometrically. I just substitute 2 in x squared. But however, the function is defined here at x equals 2. I don't care. So that's why I put x is x squared. Sorry. That's why I put x squared minus 4. I want to prove that actual 4 is my limit as I approach 2. Actually, the function value is not 4. It is 1. But I don't care about it. My functions as I approaches 4, and that's the proof. Because if I choose the minimum one here, in terms of length, like the minimum of this will be true, this will be true, this will be true, this will be true. So I'm all done. So you can give me any epsilon, I don't care. I'll calculate these two numbers, I'll take delta as the minimum, which will be a symmetric interval around 2. Okay, because I choose the minimum, then I'm still in this interval, but smaller than that. Okay, let's continue. Now there are certain things that we have stated. For instance, we have limit as x goes to c of f of x is L, and limit as x goes to c of g of x is m. Now, the sum of f of x plus g of x, the sum of the functions must be L plus m. We said that because this is one of the rules for limits. How can we prove it? Well, suppose you give me epsilon. I'm looking at some of these two functions, and I said that limit must be L plus m, so I subtract them. So let's call the function h of x. That's the sum of these two functions. The limit must be L plus m. That's the rule. I put this, but I have to prove it. So I can write this as this: f of x minus L plus g of x minus m. And that's less than or equal to f of x minus L plus absolute value g of x minus m. Now I know that these limits exist. Therefore, there should be some delta fund for this one, so that this is less than epsilon over 2. Another delta 2 for this function, so this absolute value must be less than epsilon 2 also. So you have two deltas here, delta 1, so that x minus c is less than delta 1, f of x minus L less than epsilon over 2. You can find this delta 1 because we know these limits exist. And we have delta 2, so when x minus c is less than delta 2, g of x minus m will be less than delta 2. Okay, less than epsilon over 2, sorry. So I choose delta, my delta as the minimum of this. So both are satisfied. and this is less than epsilon over 2, this is epsilon over 2, and then it's epsilon, and you're all done. Okay, let's finish it here. Next week we will continue from here on and talking about limits. Now on tomorrow, I will give you your first homework from MyLab and mastering. This first homework will be about chapter 1. That was a review of your high school mathematics. And so I will give you enough time to finish this homework within, let's say, 10, 15 days. And I will send you an email telling you your first homework is online in my lab and mastering. You can enter the site Pearson, prepared by Pearson, using in course contents. There's a link, my lab math course home, something like that. I don't remember exactly right now. You can use this link if you register to this website. You will immediately go to the course that I opened the website, and you will see your homework, and you will answer the questions in the homework. When you answer the questions, be careful. There are small letters which explain you how to give your answer. They say give your answer to 4 digits or 2 digits, or you should this like this. It may ask to give your answer in terms of intervals, so you should obey this. Otherwise, the system will give you 0 on this question. So look at how the answers is supposed to be answered in this. Okay. Any other questions?
Bitiş tarihi ne zaman olacak? Kitap daha gelmedi benim de. Benim daha şu an kodum yok da kitabım daha gelmedi. Bitiş tarihi ne zaman olacak?
Evet. Yani 15 gün olur, belki daha fazla da olabilir.
Tamam.
Olduğu için daha. Ama yani 2 gün içinde postayla gelmesi lazım. Ne zaman şey yaptın?
Yeni verdim de onun için.
Dün verdin. O sorun olmaz. So you have to be careful. Just buy your books or buy your textbooks, whatever you want, and then just follow the instruction I give in my first announcement. Open an account, then you will automatically register my class in that platform. But you should use the link in course contents to get the Pearson website. Okay. Okay, I'll see you next week on Monday, and we continue from where we left